Okay, in this section we're going to talk a little bit about slopes of curves and average rate of change. So let's draw a picture first and kind of see what's going on. So if we have a graph here and I want to find the average rate of change from, say, a point here at A, comma, f of A, and a point here at B, comma, f of B. Well, we see sort of in the midterm it goes up and then it comes down and then it goes back up. So the change, it's not always positive, it's not always negative, it kind of does a few things. But in general, what happens is I get this line through here that has a positive slope. So if it had the same rate of change from this point at A to this point at B, that rate of change would be constant. I'd get a line between this point at A and this point at B, and this slope would be the average rate of change, right? The average is, it's the middle, it's the value. If everything were the same, it'd be that value. That's kind of how we think about this. So the rate of change is the slope. The slope's pretty positive here, it's fairly negative here, then it's positive here again. Well, on average, it's positive with this m value here on that slope. So that's our average rate of change between 2 points on the graph, right? And we can find that m, well, it's the change in the y value divided by the change in the x value, which we would calculate as f of b minus f of a over b minus a, right? Change in y over change in x. And this is known as the difference quotient. And that's because it's the quotient between two differences. Difference in the y values, difference in the x values, quotient's the fraction. Okay. That difference quotient is important in calculus because of this next picture. In this picture, I'm going to do the same sort of thing. I'm going to have a point here at a comma f of a. I'm going to have a point here at b comma f of b. But I'm going to let b vary. I'm going to slide b along the curve, right? And I'm going to let b get closer and closer to a. And as it does that, this slope is going to change, right? If b is there, I get this slope. If I slide it a little bit closer, I get a slightly steeper slope. If I slide it closer yet, I get another steeper slope. And I'll call this B0, we'll call this one B1, B2. As these B values get closer and closer to A, what ends up happening is this slope gets closer and closer to the slope of the curve at this point A, right? The curve looks like it's changing a little bit faster than each of these, right? And so as these get closer and closer to the A value, the B values get closer and closer to the A value, the slope of these secant lines, these are secant lines, the slope of these secant lines gets closer and closer to the slope of this tangent line. Secant lines are lines between 2 points on a curve. The tangent line is a point on a curve. It's a line through a point on a curve that goes in the same direction of the curve. Okay, let me write that out. Secant lines are lines between 2 points on a curve. The tangent line is a line that goes through a point on the curve and has the same slope as the curve does at that point. Okay. So how do we find that tangent line? Is we find the slope of each of these secant lines as these b values get close to a, and whatever that value approaches we call the slope of the tangent line, and then with that slope and knowing that this is the point a comma f of a, we can find the equation for the tangent line. Okay, let's see a couple of examples of how this actually works numerically. Okay, so let's find the average rate of change of, let's go x cubed minus x plus 5 from x equals 1 to x equals 3. Let's see what happens here. So the average rate of change, that's equal to f of b minus f of a. It's this difference quotient over b minus a. So I'm going to take f of 3 minus f of 1 divided by 3 minus 1. So that's going to be 1/2 of 27 minus 3 plus 5. That's f of b minus f of a is 1 minus 1 plus 5. So that'll be, well, the plus 5 and the minus plus 5, they cancel. This is 0, so that cancels. I get 24 over 12, sorry, over 2 is 12. So the average rate of change from 1 to 3 of the function x cubed minus x plus 5 is 12. Okay. Let's do a slope question now. Okay. So let's find the slope of f of x equals 3x squared minus 2x plus 1 at x equals 1. So I have this parabola, it opens up. It probably has roots, but I just have this parabola. I'm not going to label what the axes are or anything, but I've got a parabola that opens up. And at some point on this parabola is the point x equals 1. And we'll draw a line here at 1 comma. If I put 1 in there, I get 2 out. 3 minus 2 plus 1 is 2. So I have the point 1, 2 on this graph. Now, I need secant lines, and I need to bring those secant lines closer and closer together so that they approach this point at 1. Okay. So let's draw one of these. Here's a point here. Here's my secant line. And what I want to do is I want to bring this point closer and closer to the point 1, 2. So if I label this point B and this point A, I want to bring B closer and closer to A. And to make that action happen, I don't want to set a specific B value. I don't want to set a specific X value for B. I'm going to call it 1 plus H, where H is how far away from 1 the point B is. If H is big, B is far away. If H is close to 0, B is really close to A. So we're going to put that variable in there, and then we're going to let that variable change, and we're going to slide it closer and closer to 0 to make B slide closer and closer to A. And so if I put 1 plus H into F, what I end up with is 3 times 1 plus H squared minus 2 times 1 plus H plus 1. And so I have this point, which has a variable in it that I get to make whatever I want, and then I have this fixed point where we're trying to find the slope of the curve at. And we're going to slide H closer and closer to 0, so the point B slides closer and closer to the point A, and we're going to do all that algebra and see what happens as H gets close to 0. So let's do some of the algebra. Our secant line slope still the average rate of change, it's still that difference quotient. It's going to be 3 times 1 plus H squared minus 2 times 1 plus H plus 1 minus 2 divided by 1 plus H minus 1. The first two bits, this guy is f of B, this is f of A, this is B, this is A, right? Okay, so let's do some algebra here. Got 3 times 1 plus, if I FOIL out 1 plus H times 1 plus H, I get 1 plus 2H plus H squared minus 2 minus 2H plus 1, and then I've got this minus 2 here, and 1 plus H minus 1 is just H. So I can do a few more things. I've got 3 plus 6H plus 3H squared minus 2 minus 2H plus 1 minus 2 over H. Let's see if anything else cancels. I've got 3 minus 2 is 1, plus 1 is 2, minus 2 is 0, so all the numbers cancel out and they go to 0. And I'm left with 6H and minus 2H is going to be a positive 4H and then a positive 3H squared. So I get 4H plus 3H squared over H. I can cancel out some H's. I get 4 plus 3H. Okay. So this is the slope of the secant line. And that's the slope of the secant line between 1, 2 and 1 plus H comma f of 1 plus H. I'm not going to write all that out again. Which on our graph is what we've drawn in this picture here. So this slope is the slope of that line segment right there. As I make H get close to 0, if we make H approach 0, I'm just going to draw an arrow towards 0. As H approaches 0, the value of this slope as h gets closer and closer to 0, this 3 times h gets closer and closer to 0. The 4 stays the same. We have the slope it's approaching 4. So the slope here of this tangent line, if I draw in this tangent line, this guy is going to have slope 4. And that's what we call the slope of the curve at a point. Okay. So now we have the basics. I'm going to do another short video talking about tangent lines a little bit more and ways to think about these slopes of the curves at different points.